Welcome my friends, welcome to my next lecture. Now in my last lecture I was introduced the notions of power series, then properties of power series, nice properties I have discussed, like if I have two power series, then what is the sum, what can I say about the product, divisions, so on and so forth. Now then I also kind of started discussion, the beautiful observation is that if I have a power series, and if I have once I have a power series, of course, then it will have a radius of convergence or you will have a domain of convergence. Now in that domain of convergence, can I say that my power series, that means it will have a sum functions. Now whether that sum function is analytic or not. So therefore if I have a power series, it will have a radius of convergence, and if I write f of z is the sum functions for the power series, because if I take any point z in the domain of convergence, it will converge, right? So therefore you can talk about, that means you have a sum functions, it is a map from your ball of center 0 or center z naught radius r, where my function I can talk about analyticity or not. On top of that, if I take the term by term differentiations of each power series term, then you can have a new power series. What can I say about the radius of convergence of that power series with the radius of convergence of the given power series, or is there any relations of the sum functions of the given power series, and by taking the term by term differentiation, you will have a new power series and the sum functions of the new power series. So these are the questions I have kind of started discussing in my last lecture. Now I'll just once again I'll just recall the definitions of like the questions, and then I'll see in a particular case, yes, the sum functions of a given power series is analytic, and if I take the first derivative or kth derivative, then the corresponding derivative of the sum functions, it exactly give you the new power series with each term is the kth differentiation of the given power series. Okay, so that's the kind of plan for my today's lecture. Okay, so as I said, so I will just start recalling the questions in my earlier lectures or the whatever I have said. So again the same question. So what can we say about the sum functions of a power series? So if I have a power series, it will have a sum function. So what can I talk about, like the analyticity or some kind of observation can I say about the sum function? So that's what the question. So let n be a radius of, suppose you have a power series which is of the form sum over n z minus z naught to the power n. And suppose it will have a radius of convergence r, and if I denote the sum functions f of z, which is sum over n from 0 to infinity n z minus z naught to the power n. Sum functions, it is well defined, because for any z in Br of z naught, that means domain of convergence, the left hand power series is absolutely convergence. That means it will give you some complex number, and that complex number I'm defining as f of z. So that these are the questions one can ask. What can I talk about the analyticity or differentiability of the sum functions? Is the series term by term differentiation? That means if I take the one times differentiation of the term of the given power series, whether it is convergent, what will be the radius of convergence? And if I write the sum functions of the one time differentiations of my term, then can I have the relations like f prime of z is exactly equal to z? That means the relations between the sum functions of the given power series with the new series which I am getting by taking one time differentiations of the term of my given power series. So what is the relations? This is for first differentiation, what will happen for k times differentiations, and what can I talk about, or what can I say about the relations between the coefficients of the power series and the sum functions f. Okay. So these are the questions, and this is the complete answers. Okay, so that's theorem I have discussed in my last lecture. So suppose you will have a power series around the point z naught. Suppose the radius of convergence of this power series is r. Then if I define my sum functions f of z, then first observation is that this is an analytic functions on the domain of convergence. That means it is analytic on a ball of center z naught radius r. Number one. Number two is that if I consider the new power series whose nth term is the k times, or I can say that I can have the term for the given power series, then I am taking the kth differentiation, then I am considering this power series, then I will conclude that the radius of convergence of this power series is same as the radius of convergence of this power series. Not only that, this power series, if I write it, this is the sum function g functions, then there is a relation between the sum function g and the sum function f. That means the kth derivative of f will exactly equal to g, and there is a relation between the coefficients and the sum functions of the given power series, my functions f. Now you see, if I take the kth differentiations of my term n z minus z naught to the power n, then depending on my number n, then that means suppose if I considering the say second derivative, and if I take the constant term of this power series, that means of course constant term will not survive, because in the first derivative itself it will be 0. So that is why, so depending on my n and which derivative I am considering, that is why this starts from n from k to infinity. That means if I talk about the kth differentiation, that means if I consider n is equal to k minus 1 term, and if I consider this term a k minus 1, z minus z naught to the power k minus 1, this term if I take the kth derivative, it will be 0. So that means it will not contribute in the sum part of my power series, new power series. That is why its sum starts from n is equal to k to infinity, because I am talking about kth derivative, or I am considering the kth derivative of the term of my given power series. Okay. So, but as I said, I am not going to prove fully of this theorem. What I will do, I will just prove this theorem only for what is called n is equal to 1. That means first I will show that yes, if I start with a power series, it will be analytic in a domain of convergence or ball of center z naught radius r, and if I take the one time differentiation of the each term, then I will have a new power series, and I will show that that new power series or new sum function is exactly equal to the derivative of the given sum functions. And of course the same conclusion is true for kth derivative, and you will have these relations fk is equal to g, and from that relations you can have the conclusion that an is equal to fn z naught divided by factorial n. Because this is true, because suppose this is true, suppose 1, 2 and 3 is true, that means function is analytic, that means infinitely many times differentiable. Each kth time derivative, if I take the kth time derivative of each term, then the corresponding new power series has the same radius of convergence of the given power series. And not only that, the derivative kth derivative of the sum functions f, which is exactly equal to the new power series, where I am considering the kth derivative of each term. Now if I assume this kind of theorem, it is true. Now from this is, you can easily conclude. Why? Because you see, I have the expression fk of z, which is exactly equal to n from k to infinity, n into n minus 1 up to n minus k plus 1 times n z minus z naught to the power n minus k, and this is true for all z belongs to Br of z naught. Now you see, look, so if I put z is equal to z naught in this expression, then what will happen? Now if I write this one, then what is that? This is fk of z naught, right? What is that? This is sum over n from k to infinity, n into n minus 1 up to n minus k plus 1, right? I am putting z is equal to z naught, that means this should be an, and then z naught minus z naught to the power n minus k. Now you see, if I take n is equal to k, then if I take n is equal to k, that means this z minus z naught to the power k minus k, that means it will be 1. Therefore there should not be any factor of z minus z naught. But the moment I will consider n is equal to k plus 1, it will have at least one factor of z minus z naught. So therefore if I evaluate fk at the point z naught, those term will be vanishes, right? So there should not be any term involving, or any term starting from n is equal to k plus 1 onwards, because if I start from n is equal to k plus 1 or k plus 2, then at least you will have one factor of z minus z naught survives, and then if I evaluate fk at the point z naught, those term will give you 0 value. So therefore only term will remain, which is that n is equal to k. Now if I have n is equal to k, then what will happen? If I have n is equal to k, then you just calculate, that means you can say that if I put z is equal to z naught in this sum, even though it is an infinite sum, only one term will survive, and that is exactly equal to n is equal to k. Because in n is equal to k, there should not be any factor of z minus z naught. So therefore it will be non-vanishing. Because if I take n is equal to k plus 1 onwards, at least one factor of z minus z naught will be there, and there if I put z is equal to z naught, it will be 0. So therefore if I put z is equal to z naught, even though this, in this expression, if I put z is equal to z naught, even though sum is infinite, only one term will survive, and which is exactly equal to n is equal to k. And if I put n is equal to k, then you will have fk of z naught, which is n into n minus 1 up to what? Up to 2 times 1, and then what will have? Ak, because this is 1. So therefore what is this? N into n minus 1 up to 1. So that means this should be factorial this n, na? So n is equal to k, so that means this should be k minus 1 up to 1, so that means this should be factorial k times ak. So therefore if I have the equality, that means you will have ak, which is fk at the point z naught divided by factorial k, and that is the relations I am talking about. Okay, so if I have the relations 3 is true, you just put z is equal to z naught in this expression, then you will have this conclusion. That means I can write my coefficients in terms of the derivative of my sum functions evaluated at the point z naught. Okay, so this expression, the last conclusion follows from the above one. But now I am going to the proof of this theorem, but as I said, I will prove the theorem not in the full generality, but I will just consider the given power series. I will show that some function is analytic on the domain of convergence, and then I will consider a new power series by taking the one-time differentiation of each term, and I will show that this power series has same radius of convergence, and if I write the function g is the sum functions of the derived power series, then g is exactly equal to derivative of f. So that's what I will prove it. So this is, as I said, partial proof. So this is my theorem. So okay, so I am starting the theorem. So without loss of generality, I am assuming the power series around the point z naught is equal to 0. So here I am assuming that z naught is equal to 0. But the same proof will work even if I start with z naught is non-zero. So that means instead of considering the power series around the point z naught without loss of generality, I am assuming that I am considering a power series as z naught is equal to 0. So that means this is my power series f of z. For simplicity of the calculations, I am doing it. So even if you start with z naught is non-zero, the same proof will work. Okay, you try it. So if I start with the functions capital F, which is n from 0 to infinity, n z to the power n, this is a power series around the point z is equal to 0. Suppose it has a radius of convergence r, then the first conclusion is that if I consider a new power series by taking one differentiation or one derivative of each term, that means if I take the one derivative, this becomes n times a n z to the power n minus 1. It will have the same radius of convergence, number one. Number two, if I write, this is my sum functions capital F, it says that the functions capital F which is differentiable or analytic in 0 to r. Furthermore, if I take the first derivative, it boils down to the functions small f, where small f is nothing but the sum functions of this series. So that means this is the like proof of the earlier theorem, but very special cases. That is why I am saying it is a partial proof. Okay, so first one part is very easy. First one is that how to check the radius of convergence same. Now if I assume that capital R is the radius of convergence of these functions, then this part is also will have that same radius of convergence. There are many ways you can prove it. So if you know this kind of results, or this is the real analysis results, limit n approaches to infinity, n to the power 1 by n is equal to 1, then since it is a convergent series, so therefore you can say that lim sup of this n to the power 1 by n is same as lim sup of absolute of n to the power 1 by n, then therefore this and this series have same radius of convergence. Or you can use the what is called ratio of coefficients. So that is also okay. For example, if you remember the formula, what is the radius of convergence? Suppose if this is the radius of convergence is r prime, what is your r prime? This is, I think, limit n approaches to infinity absolute of n divided by a n plus 1, if I remember correctly. Okay, so what is that? So this is, you can have it, right? So this is, yeah, so a n plus 1 or a n 1, let me just check once again, very quickly check. So this should be a n by a n plus 1, right? So okay, so let me just do that, yeah. So fine. So what is the power series? So this is my power series. So what is my an? So an is n, and this is n plus 1. No, I think this will not work. So you have to work with the lim sup. Okay, they have to work with the lim sup, right? Yeah. We'll have to work with the lim sup. Okay. So that means you can say that. Okay, so you can just write it. Maybe I will just write it. So what is that? So therefore, if I write the radius of convergence is r prime, what is the coefficient? Now, given power series has a coefficient n, the new power series coefficient has n. So therefore, what is your radius of convergence? So that means if I write it 1 by r prime, which is lim sup, na? So if I just look at the formula in terms of lim sup, what is the formula? 1 by r is the lim sup of that one. Okay, that's good. So if I write it that one, yes, so 1 by r is the lim sup of, this is my new coefficient, that means n times n to the power 1 by n lim sup. What is that? This is, you can write it lim sup n, that means n to the power 1 by n, then mod n to the power 1 by n. Now you see, since this limit is 1, this is convergent series, so therefore this lim sup is exactly same as lim sup of n mod n to the power 1 by n. And this is what is called 1 by r. This r is the radius of convergence of this, so therefore this will implies r is equal to r prime. Okay. So therefore, because of the fact that limit n approaches to infinity, n to the power 1 by n is 1. So if this is true, then this lim sup is same as this lim sup, and therefore this is same as this one. So therefore lim sup is same, and therefore the r is equal to r prime. So therefore the power series this and the power series this have the same radius of convergence. So this is the first observations. This is just follows from the fact or from the definitions of the radius of convergence, along with the fact that limit of n to the power 1 by n user. This is a convergence sequence. That is very important. That is why this, from this conclusion to this conclusion, is true. Okay. So therefore this has same radius of convergence. Now I will come to the what is called analyticity or differentiability. Now I will show that, so this is my functions capital F, which is, what is the domain of convergence? Domain of convergence of ball of center 0 radius r. I will show that my capital F is differentiable there, and if I take the derivative, one time derivative, it is exactly equal to the small f, which is nothing but the sum functions of the new power series by taking the one time differentiations of the old power series of each term. Okay, so if that is the case, then just look at the first pictorially. So this is my ball of center 0 radius r. So this is my capital R. Then what I will do, I will just reduce or take a smaller radius. So let it be small r. Okay, so I will consider small r, which is less than r, and then I am considering a point from here. Okay, so that means I am considering mod z, which is less than r, which is less than capital R. Okay, now if I take this kind of object, and you see, once I have a power series and I have a radius of convergence capital R, then in the domain of convergence it is absolutely convergence. And if I consider a ball of center 0 radius r, small r is strictly less than r, which is fully contained in ball of center 0 capital R, then in this domain my power series, this function converges uniformly to my sum functions capital F, right? So this is a theorem I know. So I will use that fact. So that is why it is essential to start with r which is strictly less than r. So therefore if I consider a ball of center 0 radius radius r, which is fully contained in a ball of center 0 radius capital R, and there I will have the uniform convergence. So okay, so what I will do that, so now I am starting with mod z strictly less than r, then I am just decomposing my sum functions capital F into two parts. One is Sn, that means the partial sum Sn up to capital Nth term, and then you will have the tail of the series. So that's why I am written. So Sn is the partial sum of my power series. This power series n from 0 to infinity n Zn. So this is n from 0 to capital N, and this is the tail of my power series. Then what I will do, since my power series converges uniformly in this one, so therefore what I will do, so I am considering mod z is less than r, so therefore I am considering h is another complex number such that modulus of z plus h, that is also less than r. So therefore if I consider a point z here, so therefore I am considering a small neighborhood around the point z. So therefore this neighborhood is fully contained in a disk of radius small r. So therefore if I consider a z, I am taking a little increment z plus h, and I am assuming that mod is also strictly less than r, and that I can always do that, because since mod z is less than r, so therefore z is belongs to ball of center 0 radius r, and this is an open set, z belongs to this open set, so therefore I can have a small open ball around the point z which is fully contained in ball of center 0 radius smaller, so therefore I can take z plus h belongs to that small open ball. So this is the pictorially. So if I take a point z here, this is my point z. Since this is a ball of center 0 radius r, this is an open set, so therefore I can have a small open ball around the point z naught where it is fully contained in ball of center 0 radius r. So what I will do, I will take a point here z plus h. So therefore I am considering, or I am perturbing my z with very little increment by h, so that modulus of z plus h also strictly less than r. So I need it. So that's what I have written. So if h is chosen in such a way such that mod of z plus h is strictly less than r, and that is always possible, then I will going to calculate something. What is that? I need to check that capital F is differentiable, and if I take the derivative, it should boils down to my function small f, right? So that is why I need to calculate this object. So capital F of z plus h minus capital F of z divided by h minus f of z, and what I will do, I will show that this is goes to 0, this is goes to 0 as h approaches to 0. That's the definition. If I show that this is goes to 0 as h approaches to 0, then two things will be done. One is that first capital F is differentiable, and not only that, capital derivative of capital F at the point z, which is exactly equal to f of z. So therefore I need to estimate this object. So that is why I am starting with a point z, which is mod z is strictly less than r, which is less than capital R. Then in a small neighborhood of z, I want to estimate this object, capital F of z plus h minus capital F of z divided by h minus small of f z. And my plan is to show that if I take the absolute, I need to estimate something and conclude that this goes to 0 as mod h goes to 0. Okay. So then what I will do, so I have the expression of capital F in terms of capital Sn and capital En. So then I will just do some algebra. Okay. So if I write capital F in terms of Sn and En, then first capital F of z plus h will have term Sn of z plus h and En of z plus h, right? And then capital F of z will have Snz and you have a Enz. Okay. If I do some algebra, then this object in split into two parts. One is this one, Sn of z plus h minus Snz divided by h, and then you have another part, En of z plus h minus Enz divided by h. Then minus of fz keep as it is, there I am adding, and then I am adding something and subtracting something. I am subtracting Sn prime of z and I am adding Sn prime of z. So therefore you consider these two terms together, this combine these two and this thing. So therefore the left hand side is exactly called the right hand side. So I didn't do anything extra. So I am just writing capital F in terms of Sn and En. Then I am adding Sn prime of z and subtracting Sn prime of z and do the grouping. That's it. Now you can guess what I am trying to do. So you see, now what is Sn? Sn is nothing but a polynomial of z. So therefore Sn is differentiable, right? So therefore what is the derivative? If I take the derivative of Sn, so that means this is the derivative formula. So limit h approaches to 0, Sn of z plus h minus Sn z divided by h. This is the derivative of Sn at the point z. Since Sn is a polynomial, so derivative will always exist. So therefore this difference goes to 0 as h approaches to 0 by definition of the derivative of Sn, number 1. Number 2 is this one, Sn prime minus f. Now what is Sn prime? Now if I calculate the Sn prime, then what is that? This is n from 1 up to infinity, n times n z to the power n minus 1. Now what is Sn prime of z? If this is the case, now look at fz. What is your fz? Fz is, this is the infinite series, right? N from 1 up to infinity, n z to the power n minus 1. And what is Sn prime? Sn prime is nothing but the n from 1 up to capital N, right? N times z to the power n minus 1, right? That's what it is, Sn prime, right? N from 1 to capital N, right? So that means you see that Sn prime is nothing but the partial sum of this small f. Okay, so therefore if I have a small f which is nothing but some functions of the series n z to the power n minus 1, so Sn prime is nothing but the partial sum of my series f, and I know the radius of convergence of this part series which is same as capital R. So therefore since the series is convergent in the disk of center 0 radius R, and Sn prime is the partial sum, nth partial sum of this power series, so therefore Sn prime converges to f. That is by definition of power series, because the power series has the radius of convergence of center 0 radius R. Sn prime is the partial sum. So therefore this converges to f of z absolutely in a domain of convergence B of 0, R. So therefore this is convergence by the fact that Sn is differentiable. This is convergence because I just proved that the new power series has the same radius of convergence with the old power series, and this is the nth partial sum. So the only part is remaining to check the last part. So if I prove that the last part is also goes to 0 as h approaches to 0, then by epsilon by 3 argument each component is going to 0. So therefore the left hand side is goes to 0, and then I am done. So okay. So now we will show that all three expressions on the right in the above equations will go to 0 as for large capital N and small h. Okay, so that's what I'm trying to say. So if I take limit h approaches to 0, so this is goes to 0 given fixed n, this is h approaches to 0, this is goes to 0. If n approaches to infinity, this is goes to 0 and this is also goes to 0. Both capital N approaches to infinity and small h approaches to 0. So what I will do, epsilon by 3 argument. So first I will show that, okay, choose capital N is large enough so that I can make this is less than epsilon by 2. Having chosen n, then you choose h is very small so that this and this goes to 0, then I am done. So this is called epsilon by 3 argument. So okay, so to do that, so I will do some kind of justifications to you. So therefore now, so this left hand side I will have 3 components, and now plan is to show that 3 expression on the right hand side is goes to 0 if capital N is large enough and h is very small. So how to do that? So for that you need to have this kind of expression, and that is a telescopic sum. So what I am doing is that I have 2 complex numbers a n and b n, then a to the power n minus b to the power n, this you can write it a minus b times this object. So this is, you see, if I write take the multiplication a with this one and then minus multiplication b with this one, then cross term will get cancelled, only the term will survive in the first term and the last term. So that will give you this formula. So as I said, so this is goes to 0 as h approaches to 0, this is goes to 0 as n approaches to infinity. So only part I need to kind of taken care. So this is the third one. So third one I need to do the estimate. Now if I do the estimate, so you will have enz plus h minus enz divided by h. Now enz will have expression. So this is the expression n from capital N plus 1 to infinity n z to the power n. So therefore if I put n z plus h, so therefore what will happen? So therefore you can say that, yes, so en of z plus h, you can just write it. So sum over n from n capital N plus 1 to infinity a n. So you have z plus h to the power n, and then you will have minus enz. Okay, so this should be minus n from capital N plus 1 to n a n z to the power n. If I take do some algebra, this is n plus 1 to infinity a n, then you will have what? So I think this should be plus z plus h. So therefore you will have what? You will have, so this is divided by h, you can do the algebra. So therefore this is z plus h to the power n minus z to the power n divided by h. Now if I take the absolute here, so this then absolute I can take the put absolute in the inside, that I can do that. So therefore this is n from capital N plus 1 to infinity. So your n will be there, so mod n will come out. So therefore you will have z plus h to the power n minus z to the power n divided by h. Now here I will use the above formula. If I have two number a and b, a to the power n, b to the power n, we will have this factor. Now you see, if I take the difference a plus b, what is your a here? Here my a is z plus h, and what is my b? My b is here actually z. So that is, what is a minus b? That means z plus h minus z. That means one h factor will come out. So therefore one h factor come out from a minus b, and the denominator you will have one h. So that h gets cancelled. So what will remain is that this object. So that means what is that? So this is, if I write in this way, so this is actually turns out to be in the expression. So what the expression will be there? So therefore if I write z plus h to the power n minus z to the power n divided by h, if I do that, so this is using this formula, it turns out that it should be actually z plus h to the power n minus 1 plus z plus h to the power n minus 2, then you will have what? Z and so on so forth, then you will have z plus h, then z to the power n minus 1. So this is the object. So a is z plus h and b is z. So if I take the absolute, so 1h get cancelled because of this factor, and denominator is h. So now if I take the absolute, so this is what? That means we will have the estimate of z plus h. So that means this is z plus h to the power n minus 1 plus z plus h to the power n minus 2 times mod z, so on so forth, and then finally z plus h times mod z to the power n minus 1. So that means the right hand side, if you have the estimate with modulus of z and modulus of z plus h. But you see in the starting, I am starting with mod z is strictly less than r, smaller, and modulus of z plus h also strictly less than smaller. So therefore the full object I can dominate it by, so each term is dominated by r, this is less than r, this is less than r. So if I do that one, then what will happen? I can the estimate that each term is less than modulus of r. So therefore I will have it. So therefore maybe you can just do it. So maybe if I do that, so that what will happen? This should be what? First one is r to the power n minus 1. Second one is what? This should r to the power n minus 2 times r. Then third one is r to the power n minus 3 then r square. So then at the end you will have what? R times r to the power n minus 2. Now each term will sum up to r to the power n minus 1. So this is r to the power n minus 1, this is r to the power n minus 1, this is r to the power n minus 1. Because if I add the power, you will have n minus 2 plus 1. So look at this one. This is n minus 1, this is n. So if I add the exponent of the power a and b, so it will have r to the power n minus 1. And how many terms will be there? So this is b to the power 0, this is b to the power 1 up to b to the power n minus 1. That means n many terms will be there. So therefore this is exactly equal to n times r to the power n minus 1. And that is exactly I have written. Okay, so therefore if I use this formula and if I use this estimate, this is dominated by mod n, keep as it is. So this object, that means this is nothing but, as I just explained, this is mod z plus h to the power n minus 1, then mod z plus h to the power n minus 2 times mod z up to mod z plus h times mod z to the power n minus 2. Then I am using the fact that mod z is less than r, mod z plus h is less than r. Then the right hand side I am estimated by n small n starting from capital N plus 1 to infinity mod n times n to the power n times small r to the power n minus 1. Now look at the right hand side. Now what is that? This is actually convergent series. Why? Because you see, come back here. So what is that? So you have, what is that? So this is what? This kind of series has radius of convergence is capital R. So therefore if I take mod z, which is less than small r, less than capital R, in that point z, this series is absolutely convergent. That means this is convergent series. That means n from 1 up to infinity, absolute n a n. And then if I take even just take mod z is equal to r less than r, so that means mod z to the power n minus 1, which is same as n from 1 up to infinity, n mod a n to the power r to the power n minus 1. This is convergent because of the fact that this series has same radius of convergence with my original series, which is capital R, and small r is strictly less than capital R. And if I take a point mod z, which is exactly equal to r, which is sitting inside ball of center 0 capital R, so in this point my series is absolutely convergent. So therefore this is a convergent series, and this is same as this one, and this is nothing but this series. So what is that? Now look at, this is the tail of this series, n from 1 up to infinity, n a mod a n times n times r to the power n minus 1. Now this is convergent, I know. So if this series is convergent, so what will happen with the tail? So tail will go to 0 is capital N approaches to infinity, right? So therefore now I am done. So therefore the estimate of the third term, this is goes to 0 as capital N approaches to infinity. This is also goes to 0 as capital N approaches to infinity, because of the fact that the radius of convergence of the sum functions or of the power series by taking 1 times differentiation is the same radius of convergence with the given power series, and Sn prime is the nth partial sum. So therefore this is goes to 0. This is goes to 0 as h approaches to 0. So therefore by epsilon by 3 argument, you see the expression on the right hand side is the tail of the convergent series. So this is the tail of the convergent series. And why the series is convergent? Because of the fact that this series has the same radius of convergence with this series. That is the fact. That is why. Because mod z is small r, which is strictly less than capital R, and this series has the same radius of convergence with this series. That is why. Okay. So if these things combine, therefore given epsilon, we can find capital 1 large enough. If capital N is less than capital N1, then I can make the third term of the expression is less than epsilon by 3. Then once I have one n1 I will get, and another n2 I will get, because this converges absolutely, Sn prime converges to f of z absolutely. There also I can have the existence of n2. So therefore I can make the second term also less than epsilon by 3. Having chosen n1 and n2, if I choose capital N is the maximum of n1, n2, then once I fix the n, then I go to h approaches to 0. So now if I fix n, so that means you can take n is nothing but maximum of n1 comma n2 plus 1, then n is this, then means both estimate of the last two terms holds. So now if I consider the Snz, which is a polynomial, and the derivative of a polynomial is obtained by taking term by term. So therefore, since capital Sn is a polynomial which is differentiable, so therefore this first expression I can make less than epsilon by 3 whenever mod h is less than delta. That means very small. Now if I combine these three things, then I can say that the whole left hand side estimate I can make less than epsilon whenever mod h is less than delta, and that is the kind of conclusion is that capital F is differentiable and derivative of capital Z is exactly equal to small z. Okay. So this is called epsilon by 3 argument. This is very nice. So first thing is that you just break this object into 3 parts. So this is 1, this is 2, this is 3. So this first you conclude that this is goes to 0 as n approaches to infinity, because of it is a tail of the infinite series. This is also converges to 0 because it is nothing but the nth partial sum of the convergent series. So I'll first fixed n by choosing this is goes to 0 and this is goes to 0. Having chosen n, then I'll choose h is very small, so that this term also goes to 0. So therefore if I estimate for each 3, then I can say that this absolute is dominated by less than epsilon whenever mod h is less than delta, and that will by definitions of the derivative of capital F is differentiable and derivative is small f. One small corollary I have said, this though I am talking about I have proved only for the existence of first derivative, but the functions capital F is infinitely many times differentiable, and higher order derivative also a power series obtained by term-wise differentiation and has the same radius of convergence. That means if I consider a new power series which is nothing but a n z to the power n to the power kth derivative, okay, it may be instance from k to infinity. So if I write this is a kth derivative, right? So if I write this is the kind of some function g, so this series has same radius of convergence with that series. Not only that, if I write that this is the sum functions capital F, so kth derivative of capital F is exactly equal to g, and in fact that is the statement I have given in my earlier slides. Okay, so therefore what I have observed is that if I have a power series around the point z0, and if I have the domain of convergence say B of z0 comma r, ball of center z0 radius r, in that domain my sum functions is analytic. Not only that, if I consider a new power series by taking the kth differentiations of each term of the given power series, then the new power series will also have the same radius of convergence with the old power series. Not only that, if I take the kth derivative of the sum functions of the given power series, it exactly equal to the sum functions of the after taking the kth derivative of the given power series. That means fk is equal to g. And last conclusion is that I can write my coefficients in terms of the derivative of the sum functions of the given power series, and that actually follows, I have already explained, that actually follows from these expressions. Okay, so therefore I have proved only for partial proof I have given, so that means by taking one first derivative, but as I said you can just proceed the same process with the kth derivative also, you will be able to prove everything. Okay, so some examples of the previous theorem, as I said. So for example, the power series, it will have the radius of convergence. I already told you this radius of convergence is infinity, and then I already said that. So if you can guess what is the corresponding power series, or what is the sum functions of these power series. The sum functions of these power series is nothing but sine z. Now since it is a radius of convergence is r is equal to infinity, that means this function is analytic everywhere in the complex plane, and you know sine function is the function which is analytic on the everywhere complex plane. So therefore, so in terms of power series, this is the corresponding series expansion around the point 0. It is very important. So this is a power series around the point 0, and the sum function is exactly equal to the sine functions. So there are many ways you can do that, or you can say that this is a power series. So what is the sum function? Sum functions, you just say there is a relations with the coefficients and the sum functions. Now fn at the point 0 divided by factorial. If I calculate that one, then you will end up with this is the sine functions, right? So therefore the power series has radius of convergence r is equal to infinity. The sum function is nothing but the sum functions. Now, kind of advantage of having this term by term differentiation is possible, because if I have a power series of the sine functions, then you can have the power series of the cosine functions. So therefore, sine functions power series, I know this is my power series of the sine functions. Now if I take the derivative, of course the left hand side is nothing but cosine functions, but just by the way I have defined sine functions in terms of exponential functions and Euler's formula, so you'll have the derivative cosine functions. Now what will be the corresponding power series? By taking the one time, just by earlier theorem I have said, if I have a power series, if I take the first derivative of each term, then the same radius of convergence. Now since the radius of convergence of this power series is infinity, so therefore if I take the one time derivative of each term, it will also have the radius of convergence infinity. That means it is analytic everywhere in the complex plane, and the left hand side is the cosine functions. So therefore this is the corresponding series expansion of the analytic function cosine z around the point z is equal to 0. So you see, observe that this is the series also the radius of convergence is point at infinity. So therefore this is another advantage. Like, so if I have a like power series, and if you know the expressions, then you can have the power series of the derived functions, because they will have the same radius of convergence. So like if I know the sum functions of this power series, which it turns out to be sine functions, then I can have the expression of the series expansion of the my functions cosine functions around the point z is equal to 0. This is the one times derivative if I take. Now there is a note I have written. So in the previous theorem, like term-wise differentiation of a power series, namely term-wise integrations. Like if you can recall, when in real analysis, when if you talked about the convergence of a series of functions in uniform convergence, term by term differentiation is possible. Now whether term by term integration is possible or not. Now as I said, so if you just recall the concept of what is called uniform convergence for series of functions, then term by term integration also possible. That means if I have a series of functions sum over fn, so if I have a series of functions, think about real valued functions. If I have a function sum over fn which is converges uniformly to a sum function g, and suppose each of the functions fn's are Riemann integrable on the closed interval a to b, then if I take the integrations of a to b sum over fn n from 1 to infinity, then you can push the integration inside the summation. That means term by term integrations is possible. That is possible, provided the convergence of the series should be uniform. That is very important. So therefore, since term by term differentiation I just discussed in my earlier slide, so given a power series, if I take the kth derivative of each term and having a new power series, then the corresponding power series has the same radius of convergence, and if I write the new power series sum function is g, then the original power series sum function, if it is f, then the kth derivative of f is exactly equal to g. That means term by term differentiation is possible. Similarly, you can ask the term by term integrations. I am saying that this is also valid for power series, though I am not kind of explaining clearly, but term by term integration is also possible. For example, if this is the possible case, then if I know the power series expansion of cosine, then I can have the power series expansion of sine by taking the integrations. So by doing term by term integrations of my power series cosine, we can have the power series of sine functions. So therefore, since term by term differentiation is possible just by earlier theorem, then if I have a power series of sine around the point z is equal to 0, then I have the power series of cosine. Now since term by term integration also possible, therefore if I have a power series of cosine, then I can get back the power series of sine functions. Okay, this is just a note, though I have not discussed explicitly why term by term integration is possible, but it is possible. You can consult with some books. But the derivative part I have discussed. Term by term differentiation is possible, yes. Okay, so I think I should stop here. So this is one-sided I have proved. So that means maybe I can just think about, you can just, that's why I'm saying to think, you see. So last theorem says that, look at the last theorem, it says that given a power series, its sum function is analytic and hence infinitely many times differentiable in the disk or domain of convergence of the power series. That's what I have discussed. So therefore, if I have a power series, if I have a domain of convergence, if I write the sum function is small f, then it is analytic, that means it is infinitely many times differentiable, right? So now the question is converse of the above statement. What is the meaning of above statement? So therefore, if I start with a power series, the sum function is analytic in a domain of convergence. Now I am asking the converse. So I am starting with the analytic function on some domain, nice domain, and I am considering a point inside that domain. So therefore, by definition, it is analytic at that point, right? Now the question is, can I have a series expansion around that point? So this is the question. So now think about the converse of the above statement. This is my questions. So now I am starting with open set. I am starting with a point. Given that fz is analytic. So earlier I am starting with a power series, considering the sum functions, then I am saying that it is an analytic functions. Now I am asking the converse. I am starting with an analytic function on some domain. So D is an open set, z0 is a point in D. Suppose f is an analytic functions. Now the question is whether can I have a power series representation around the point z0? That means, can I write my f in terms of the power series in a neighborhood of z0 for some r? And the answer is yes, you can do that. And if it is so, suppose you can write, then the question is, can I have another power series? That means, is there more than one such power series possible? That means, whether can I have a unique power series representations, or can I have more than one power series representations? So answer is that yes, you can have the power series representation around the point z0. Moreover, it is unique. So therefore, if my functions f is analytic in a domain D, if I take a point z0 inside D, then I will have a power series expansions of my functions around the point z0, and it is unique. And that is called what is called Taylor's theorem. So that's what it is. So maybe I will come to my next lecture. So that means the converse of this earlier theorem, that means the Taylor's theorem. That means if I have analytic functions on a domain D, if I take a point z0 in D, then I will have a power series expansion around the point z0. Now this is a very powerful theorem. Why? Because you see, in real analysis you can have the example of like functions which is like infinitely many differentiable at some point. But if I say that, can I have the explicit expressions of f around that point? Suppose you have functions from R to R, and if suppose you have some, I will give some kind of, or maybe I am saying that. So start with the functions from R to R, and at some point or in a neighborhood of, in some open set, suppose your function is infinitely many times differentiable. Can I say that if I take a point inside that nice domain, and I will have the explicit expression of my functions? In real analysis, you cannot have that kind of things, right? So, however, in complex analysis, if I have the analyticity, but you cannot always say in real analysis. In special cases, you can have it, right? But come to the complex analysis setting, that means if I have a functions f, and suppose you have a nice domain D, and your function is analytic, then if I take a point z0 inside my domain, then around the point it will have a power series. That means I know the explicit expressions of f, or I know my functions f locally. at the point z0 in terms of power series. Power series means what? That means it is nothing but the limits of the polynomials. That means it somehow, if I know the polynomials, that means I know the behavior of the limit of the polynomials. That means I know my functions f locally. And that means what? That means the property of analyticity is very rigid. So that means if I have the analyticity in a domain, and if I take a point inside the domain, then I can have the explicit expression, or locally I will have the expression of my f in terms of the polynomials. I can do that. That is the beauty of what is called analytic functions. In fact, some of the books it says like that. So I'll say that my function is analytic at a point z0 if and only if it will have a power series expansions. But I started with something else. Like I'm starting with some definitions, complex differentiability. Then I am saying that look, if I have analytic functions on some domain D, and if I take a point z0 in D, then around a point z0 I can write my f explicitly in terms of power series. That means I can write I can have the I know my functions there in a neighborhood of z0. No means what? So I know a power series. Power series means it is kind of infinite sum of polynomials. So therefore, if I know the polynomials, that means if I take the partial sum, it will be a polynomial, right? And it converges to my functions f uniformly in some nice domain. So therefore, I know the expression of f explicitly in a neighborhood of z0, and that is very beautiful. So, but for that I need what is called my functions f should be analytic. So that means analyticity, as I said, many things earlier also I said. So analyticity is a very rigid property. So if my function is analytic in a domain, then at a point z0 inside that domain, I know the explicit expression of my f. That means I can write my f in terms of power series. So that is called Taylor's theorem. In my next lecture, I will start with the statement of this theorem, and I will show that yes. So if I have analytic functions in around, it will have a series expansion valid around the point z0. That means I can write my functions in terms of power series, that is called Taylor series. So I think I should stop here. So in my next lecture, I will start by answering this question. Yes, the questions I posed here, answer is yes, you will have a power series expansion around the point z0 inside the domain where my function is analytic, and you will have a unique power series. Okay, so I think I should stop here. In my next lecture, I will start with the statement of Taylor's theorem and its proof. Thank you.